to an end. And the fifth ELGA is also coming to an end. And we will end with the last lecture of Charles Favre on B-divisors in applications to dynamics.
Okay, I promise there will be some dynamics. Okay, so the idea today is to give some application of B-divisors. So first to some duality problems. So I'll try to explain the proof of the theorem I stated last time, and then to turn a little bit to dynamics. So recall that X is my favorite smooth projective variety over C of dimension D. So probably I'm going to assume D at least 2, probably 3, and so on. So I'm going to be interested in the duality of cones naturally defined in the space of B-divisors. So let me recall a couple of things. So we were considering various cones in the real neural series space of X. So we had the Neff cone, which is, if you want, the space of the closure of the ample cone. And we consider also the pseudo-effective cone, which I define as the closure of the big cone, or if you want, the closure of an effective cone. Sorry? Yep. So a good start. Okay, so what I mentioned is that, okay, so the second thing is that you have a pairing also from neural series space to the numerical classes of curves that denote by nd minus 1 to R. And then this pairing is perfect. And so these two real fine-dimensional real space, vector spaces are in duality. And so it's natural to ask what is the dual cone of the Neff cone and then a pseudo-effective cone. Okay, so for the Neff cone, it's essentially by definition. So the characterization of the Neff cone is also the space of divisors of divisor classes such that the intersection with all curves is non-negative. So you can view this as a duality statement. So if you define the pseudo-effective cone of curves, so let's say the closed convex cone generated by classes of curves, then this says that the Neff cone is in fact the dual of this one, of the pseudo-effective cone. So I put a dual like this. So in other words, this is a set of classes in N1 such that for any beta in this cone, the intersection is non-negative. Okay, so it's kind of natural to ask what is the dual of the pseudo-effective cone. So the answer was given by the famous paper by, referred usually by BDPP, so Buxom, Demey, Pound, and Peternel. And this is what I'd like to explain now. So they characterize the dual of the pseudo-effective cone. So here, if you want, I should have put exponent 1. Okay, so in the end, it's going to be the set of movable curve classes. Okay, so let me give one definition. Let's say So it's probably a local definition here. Strongly movable curve class. What's going to be? Well, it's going to be the push forward under, so let's say class in ND minus 1. So I'm going to say that it's strongly movable. It's a push forward under a birational morphism of a complete intersection. So if alpha is the push forward under some pi is a proper birational morphism of some curve classes, which is of complete intersection. So let's say alpha 1 dot alpha 2. So here I guess it's alpha d minus 1, where alpha I are ample or nef, let's say ample. I didn't define movable, so it's let's say it's a local definition. So I'm really interested in the closed cone generated by this. I'm not going to define various definition of movable that you can appear in the literature. Okay, so let me define mov of X is going to be the smallest closed convex cone inside ND minus 1 that contains all these classes. So with the closure of the convex hull of all like strongly movable classes. So this is, yeah, sure, sorry. So in particular, it contains, so you can take pi to be the identity. So this cone contains the complete intersection classes, but much more, okay? And the statement of Buxom, de Mailly, etc., is that the dual of the pseudo-effective cone is in fact this movable cone. Let me put exponent to indicate where I'm living. So it's inside here, and d minus 1. Okay, so why am I talking? So in fact, the proof relies on several ingredients, and in particular, it relies also on Fujita's theorem. Okay, so it's this statement is very, very connected to everything I talked about before, but and it uses the orthogonality relation that I was explaining last time also. Anyway, so I'm talking about this because this suggests to introduce so the following definition of let's say the movable cone, but in the space of B-divisors, in the space of B curve classes. So I'm going to define for definition of so in the space of Wahl curve classes. Okay, so remember I defined the nef cone in the space of Wahl divisor classes as being the closure of Cartier nef classes, and I mentioned that this is the same as the Wahl divisor class was such that for any pi, this alpha pi is nef in codimension 1. So here I'm going to use the same kind of thing. So I'm going to define the space of curve classes such that for any pi, alpha pi is going to be strongly movable. Okay, so it's going to play the role of the nef cone of the nef B-divisor classes. So let me so let me define this. So BPF, I'm going to explain later why this is like this. So this is smallest closed convex cone in this enormous space that contains what? That contains, let's say, okay, well, yeah, well, okay. Such that contains any classes, curve classes, that are complete intersection. So let's say alpha I or ample class in some model X pi. Okay, maybe I should. So it's kind of analogous to the definition I did of the Neff cone. This was the closure of the space of Cartier classes, alpha, such that alpha is Neff in X pi. Okay, so here I'm saying essentially the same, except that I'm replacing like Neff or ample by complete intersection classes. Okay. So there is a fact is that you can recognize. So if alpha is a class in this BPF cone, so BPF stands for base point free. So you can, well, maybe what I could say is that you can define in an analogous way the some positive cone in any codimension. Okay, but I'm only going to use the Neff cone and this BPF cone of curves. Okay, so I mentioned that a Neff class can be recognized by looking at alpha pi being, by the fact that alpha pi is Neff in codimension 1. Here it's the same. So alpha is base point free. It is in this cone if and only if for any pi, alpha pi is movable in this sense. Okay, so and you can show also that for the natural, so it's a closed convex cone, and just like the Neff cone, it has a compact base for the natural topology on this space. Okay, so now I'm going to consider a Neff class, a general Neff class, and I was interested in looking at its intersection with itself to power d minus 1. So remember how I defined this. So there is this theorem that alpha being Neff, you can construct a sequence, decreasing sequence of Neff Cartier class alpha n, decreasing to alpha. And by definition, this is a decreasing limit of this alpha n to the d minus 1. You can always assume that your alpha n is not only defined by some Neff class in some model, but you can assume that alpha n is in fact determined by some ample class in some model. So all these guys are in this cone. And so by taking the limit, this d minus 1 power of alpha is in the BPF cone. Okay? And the claim is that, in fact, this map essentially gives you bijection between these two cones. So you have to be a little bit careful. So I cannot state like it's a bijection between the interior of these two cones, but the right statement is as follows. So let's say that an F class is big if, well, so if alpha were just Neff in some model, to be big is saying that its volume is positive, right? So alpha to d is positive. So here I know how to define this. So I'm going to, just by definition, alpha Neff is big if its top intersection class is positive. And then similar way, so if I have beta, which is a BPF, a curve class, I'm saying it's is big. I cannot really talk about volume, etc., but it's going to be big if it dominates some complete intersection class. So if there exists an epsilon positive, or maybe I don't really need this. So there exists some ample class in any model, so maybe in X or X pi, such that beta is greater or equal to the Cartier class omega d minus 1. Okay? So I have to think, of course, that omega needs to be, it's going to be very, very small, right? So remember, so if you have a line bundle, it's big if and only if it's more effective than some ample line bundle. So the definition here is some kind of the natural analog for curve class. Okay, so now I can state the theorem. So we proved it a couple of years ago. So it's not really a duality statement, but almost. So it says that if you look at the map from the space of nef B classes, codimension 1 classes, that are big, to this BPF cone of curves, again, that are big. So alpha maps to alpha d minus 1. Then the statement is that this is a bijection. Okay, so we'd like to have a bit more like homeomorphism or something like this, but it's not completely clear to us. So we only have the fact that this is a bijection. So remember that, I mean, all these kind of things have this intersection here of some kind of continuity properties, but only along decreasing sequences. And it's not, a priori, it's not continuous for the canonical topology on that space, so we don't know if it is a homomorphism or not. So, is it a homomorphism? It's not clear. Yeah, of course, maybe if D is at least 3, right? So the second thing is that, okay, but yeah, you have a statement like this. Maybe, in fact, there is a similar statement, but working directly on X. So you start with the nef class, you look at this, then you land in this movable cone, etc. Is it a bijection? In fact, in general, no. So this is, the claim is like this. So the statement cannot be true at a finite level. Well, okay. In general, I mean. So that this kind of statement can only be true at the level of B classes. So why is it so? This is an observation by Lee. Is that if you have a big line bundle, whoops. If you look at, so you can look at its function class, and you look at the nef envelope of this. Okay, so the nef envelope is, lies in its nef. And the observation of Lee is that if you look at its d minus 1 power, it's always Cartier. But then there are some examples of Nakayama for which the nef envelope is not Cartier. It's really a B-divisor that is really, it can not define at a finite step. So what it means is that if you take this class here and you look at its d minus 1th root, it's something which is not, I mean, this class is determined in some fixed model, in fact in X, but it's d minus 1 root, it's the envelope of this guy, it's something that you need to look in all birational models over X. Okay, so here, it's bigness, yeah. So I'm not sure, maybe it's a bit counterintuitive. But, so yeah, and yesterday, so I explained that this, in the toric case, this boils down, this result boils down to a Minkowski theorem. Well, I didn't explain, but about realization of polytopes with a fixed codimension 1 faces. Okay, so what I'd like to explain is a little bit how this statements work. So you have two things to check. So there are first the injectivity, or first. Okay, well, on the one hand, the injectivity, on the other hand, the surjectivity. Okay, and both are quite interesting. So I'm going to use. So the deepest part is the surjectivity. So well, it says that you take a class like this, a curved class, and you need to produce a divisor class whose d-1 power is this one. So it's not completely clear how you would do that. And we're going to follow an approach that is very similar to a proof of Minkowski theorem, which is due to Alexandrov. So apparently there are many of them, so, but it's variational in nature. Okay, so how about the injectivity? So it's not a complete proof, it's just an indication how it works. So, okay, so you take two Neff classes, and you assume that alpha d-1 is equal to beta d-1. Okay, so what does it say? It says that if you can, so this is a curved class, you can cup with alpha on both sides and with beta also. So in particular, you get alpha d is equal to beta d-1 dot alpha. And you also get, well, the symmetric information. Beta d is alpha d-1 dot beta. And you need to show, well, in that case, two classes are equal. So here it's essential to assume that both alpha and beta are big. Okay, so the first observation is that the function where you look at the successive intersection of alpha and betas, where k is increasing, so k between 0 and d, this guy is concave. Okay, so let me draw something. So maybe here is k. And here we're drawing log of alpha, the intersection number alpha k and beta d minus k. Yeah, maybe I should have said, so because these classes are big, all these intersection numbers are going to be positive. So, okay, so for k equals 0, here you have d minus 1, you have d. So what is this value for k equal to 0? You're looking at log of beta to the d. The second one is maybe log of alpha dot beta d minus 1, et cetera, et cetera. And then you have same thing here. So this is log of alpha to the d. And here is log of beta alpha d minus 1. Okay, but what are our assumptions? So we have these two equalities. So it says what? It says that these two things have to be the same. I'm not sure, here and here. And these two things have to be the same also, right? Okay, and what I was claiming here, so I'm going to explain why this is true, is that this sequence of points, it needs to be concave. Okay, so the only way it has to be is that they're all equal. Okay, so this implies alpha d, well, alpha k, beta d minus k is constant. So it's alpha d, it's beta d for all k. And then you can, once you know this, you can use, so I didn't explain, but you can use some version of discount inequalities to show that they are actually equal. Okay, there is some trick that implies that alpha is equal to beta. So I'm not going to explain this, but so it's like a reverse of Brun-Minkowski's inequality for mixed volumes. in the case of in algebraic geometry. Anyway, so how do we see that this is this sequence of numbers is log concave or is concave? Well, it boils down to, so this is a consequence. So the fact that alpha k beta d minus k is log concave follows from Hodge index theorem. Okay, so let's suppose that d is equal to 2. So what it says that, so Hodge index theorem in the case where alpha and beta are nef, it's the same as Cauchy-Schwarz, but reversed, right? So all the intersection to the square is greater or equal to alpha square and beta square. It's exactly this. Okay, so this says, now you transfer this. This is exactly this statement in the dimension 2. And how you deal with a higher dimension? Well, you slice by, so you apply this result, and then you slice by a generic section. So you may suppose alpha and beta are ample, and you slice successively by hyperplane sections. So this, so this thing is kind of elementary. So the fact that it's a log concave is true. You need not to be big. It's true for any nef classes. But then, of course, this thing here, this kind of inequality holds only for big classes. So I didn't explain, but here you need to use C1 differentiability. This is one crucial of the volume. This is a crucial ingredient. Okay, so we have injectivity, and now we need to show the surjectivity. So we use the variational method. Okay, so what does it mean? Okay, so we take gamma, a curved class, which is big inside BPF here. So base point free class, which is big. So let's say that gamma is greater or equal to, let me state, omega d minus 1, where omega is ample. And we are going to optimize or maximize the volume of some curved class in some specific compact set. So it works like this. So let me introduce K, which is the set of nef classes whose intersection with gamma is, let's normalize by 1. Okay? And then the idea is to look at the map on K. So look at the following map on K. To any class, you look at its volume. Alpha to, well, let's say volume. Alpha to the D. Okay? Okay, so it's not completely clear. So what is K? So yeah, it's something infinite dimensional. So you know I have some difficulties to draw these kind of things, but so let's assume that this is a nef cone, and somehow what we're doing, we're taking a slice here. This is supposedly K, and we're going to optimize this function in K. We're taking a point where this number is maximal. It's somewhere here. And for some reason, this point where it's maximal, where any point where it's maximal is, in fact, is going to solve our equation. So if so the claim is that first, this function admits a maximum. Let me give it a name. I don't know. It's like a volume, so, okay, vol. So vol admits a maximum, say at a point alpha star. And second, well, when I look at alpha star to power d minus 1, this is this curve class gamma. Okay, that's so that's the variational method. Okay, so I need to tell you why this volume function admits maximum, and why do you have this. So here it's so I wrote k because surprisingly enough it's going to be compact. So it's compactness property. And why do you have this? This is a C1 differentiability. Okay, so let me explain in more detail. So so we wrote this paper a couple of years ago, and I reread the proof yesterday or 2 days ago. And in fact, there are a lot of tiny details. Okay, so I'm going to be quite sloppy, but. Okay. Okay, so maybe why k is compact. So here you use this this assumption here, is that if alpha dot gamma is equal to +1, then by assumption gamma dominates some ample class. So you have that. This is greater or equal to alpha dot omega d minus 1. And now, so you intersect your Neff classes with a Cartier class. And so this is something which is continuous. It's always positive. And so this set, the set of Neff classes for which you're bounding the intersection with some big and Neff class is something which is compact. Is compact. So if you want, so maybe it's not so clear for you, but it boils down to the following fact. So if you take any birational proper morphism, x pi over x, what I'm saying here is that you look at the space of Neff classes inside x pi, such that the intersection of alpha with what? With the pullback of omega to d minus 1 is bounded by 1. This is compact. Okay, so the key point is that, okay, maybe this guy is not ample, but it's Neff and big, so it's sufficient to ensure this. Okay, and then you need to check that, so there is a subtle issue here, is that the volume function from k to r plus is weakly continuous. So it's continuous for the natural topology on K. Well, and I'm not going to do that, but it's possible to prove this. And so you have a continuous function. It admits a maximum on the compact set, so it admits a maximum. So in fact, you don't even need the continuity. You need the function to be semi-continuous. In which direction? Upper semi-continuous, I guess. Okay. And so, yeah. Okay, so now how do you check this, this thing, right? So you do as follows. So you pick by duality, you only need to take your favorite Cartier class, and what you want to check, you want to prove that this class alpha star d minus 1 intersected with beta is equal to gamma intersected with beta. just that the pairing between Cartier classes and Wahl classes is perfect, as I explained in the first lecture. So why is it true? Okay, so this is your alpha star here. And beta is going to give you a direction. And you're going to estimate, well, this volume function along alpha star plus t beta, okay? Except that there is a slight issue, so we estimate the volume of alpha star plus t beta for t small. So we know, you have to be careful because you want to stay inside K and use the fact that alpha star is a maximum. So you have to divide by the right factor such that this stays in K, okay? And then you use the maximum in the sense that since the volume function is C1 differentiable, if it is maximum, then the differential is going to be 0. Okay, so you get the estimate, and at the end of the day, you get this. Okay, let me do it like quickly. So in fact, we're not going to play with the alpha star plus t beta, but something close. So there is another issue, is that this guy a priori is not nef. I mean, beta is anything. Okay, so. Yeah, well, okay, so you have to take the nef envelope of this, and I want this to be, so this is an F class, I want this to be inside K, so I have to divide by its intersection with gamma. And oof, this is in K. So now let's compute the volume at the first order. So when t is equal to 0, alpha 0 is our original alpha star. Okay, the envelope of alpha star is already nef, so it's itself. So what you know is that the volume at the point alpha star is bigger than the volume at alpha t, which is a huge intersection number, so it's something like p alpha star plus t beta to the d divided by p alpha star plus t beta to the dot gamma to the d. And now I'm using this, the fact that I know that this thing, so this thing is the volume of this class, so I know that this is differentiable. And so I'm going to use only this sum inequality. So the volume of this, so it starts with the volume of alpha star. And then at first order is something like t times d times alpha star d minus 1 dot beta plus small o of t. Okay, so the volume at the point alpha star is, the differential of the volume at point alpha star is exactly that linear form. So this is what I proved last time. And then this nef envelope is, so it's less or equal to alpha star plus t beta by definition. Gamma is BPF. So you have, so this intersection number is less or equal to, so 1 over is greater or equal to this number, alpha star plus t beta, dot gamma to the power d. Okay, so I let you do some analysis. And what you get in the end is, yeah. So remember that alpha star d dot gamma is 1. So if you look at the first order expansion of this, okay, well, you have the volume plus dt times this guy. And then by looking at what comes from the denominator, it's exactly beta dot gamma plus O of t. Okay? Exercise. Okay, so I know that, what did I do? Yeah, so, okay, sure. So hopefully, so this implies that this thing has to be, okay, I didn't discuss really about the sign, so let's play with the t positive. So this is going to imply that this guy has to be non-positive, and then you play with t negative. It has to imply that this guy has to be a various sign. So at the end, you show that these two things have to be equal. Since it's true for any beta, well, you have proved what you wanted, that this is equal to gamma. Okay, so it's far from being constructive. And, yeah, so this is, so this concludes somehow what I wanted to tell you about the duality statement and so on, and differentiability of volume and Neff classes. And now I'd like to, so I have like 45 minutes or so, yeah, right? So now I'd like to turn to something more dynamical. So application to okay. So again, so X is a smooth projective variety defined over C. Can even, the main examples is X to be the projective space over C. And you take any rational map, rational self-map from X to itself. We're going to assume, to avoid trivialities, that it's dominant, so essentially it's surjective. So for instance, if F is birational, this is perfectly fine. We're in business. Okay, so I'm going to do dynamics. So I want to consider the iterates of this map. Okay, so I'm going to denote them by exponents here. So Fn is F composed with F composed with F n times. And there are many things that you can ask about this. So I'm going to look at one natural invariant that comes from algebraic geometry that is attached to F, which is its degree. So I'm going to focus on the behavior of the degree of the iterates. Okay, but first I have to define what is the degree. So the degree of a map depends on the choice of some ample line bundle on X. Okay, fine, so let me fix some ample line bundle. So probably if you're over a complex project space, you choose L to be O of 1. And let me denote by omega, it's a first-gen class. So it's an ample cone. So the degree of F, well, this is the intersection of the pullback of omega with omega d minus 1. Okay? So in the case where F is, where X is a projective space, F is defined in homogeneous coordinates by d plus 1 polynomials of the same degree and without any common factors. And the degree of F is exactly this degree, right? So this is an integer, positive integer. And the question is, what is the behavior of this sequence? Especially, so in most cases, you expect this sequence to tend to infinity, and so we are interested in the asymptotic of this. Okay, so you may wonder, why is it so crucial or interesting to look at this? Is that this sequence of numbers, it controls the volume of the graph of Fn, and so in turn controls a lot of crucial quantities attached to F, in particular the entropy, Lyapunov exponents, blah, blah, blah. Okay, so somehow understanding just the sequence of numbers is like the first step if you want to get further and do deeper, to get deeper insight into the dynamics of F. Okay, good. So I've described a lot of tools since during my lectures, and so using this, I can show quite quickly, for instance, that Hsu's criterion of bigness. Well, this implies that the sequence of degrees are submultiplicative. So there exists a constant C such that the degree of Fn plus m is at most constant degree of Fn times degree of Fn. So again, in the case of the projective space, this is completely elementary, but then this is true, in fact, over any projective variety. So before I give a very quick proof of this, then you can use Fichetti's lemma. So if you multiply by C here and there, what you see is that this sequence of numbers is submultiplicative. Okay, so when you have a sequence of positive number that is submultiplicative, you can look at its nth root. This converges to some number that we, in fact, it's that we denote by lambda 1 of f. It's called the first dynamical degree. And this is a quantity which is very much related to this entropy of the map and so on. So it's a very crucial quantity to look at, maybe the first basic quantity to look at. Okay, so I'm going to state one theorem next about the relation between this degree of Fn and lambda 1. Okay, so before I do this, I'm just explaining this arrow here. Okay, so what is Hsu criterion of bigness? Remember, it tells you that if alpha and beta are F, then the volume of the difference is greater or equal to this quantity here. So alpha d minus d alpha d minus 1 dot beta. So if it turns out that this thing is positive, then the volume of the difference is positive, so alpha minus beta is effective. Okay, so you turn this around, and the consequence of this is an inequality for any alpha and beta nef. Beta is less or equal to alpha times d, what is it, alpha to the d, alpha d minus 1 dot beta. Okay, so this is a really direct consequence of this. Okay, so how do you use this to infer the submultiplicativity? Well, you do as follows. Yeah, so you look at Fn star of omega, and you compare this class Fn star of omega with, so beta is going to be Fn star of omega, and alpha is going to be omega. So it's omega, and you have d over the volume. And here what you get is omega d minus 1 dot Fn star of omega. Oh, fantastic. So this is exactly the degree of Fn, right? This is a constant. And now you pull back by Fm. So this is a constant times degree of Fn times Fm star of omega. And now what you do here is you cap with omega d minus 1. You get exactly this. Okay? Okay, so if you're, I cheated here, okay? So I cheated because I didn't tell you why this pullback of an ample class offered by a holomorphic morphism is fine. It's going to stay in F. But by a rational map, there is no reason why it stays nif. Okay? But in fact, so this is still true if you look at this as a Cartier class. So omega is a Cartier class in this B-divisor stuff, and by a rational map, there is a canonical action on the space of Cartier classes, which preserve the nef cone. So all this computation here are in fact perfectly fine if you work in the space of B-divisor. Okay, so let me continue my story. I'm completely lost about the time, so it's like what, like 8 minutes or 13 minutes? Almost 40 minutes. 40 minutes, okay. Yeah. Okay, so the story continues like this. So instead of looking at this degree here, where I'm looking at pullback of omega d minus 1, I could have introduced like intermediate degrees, where I'm pulling back omega to the k times omega d minus k. Okay, so let's do that. So you can play exactly the same game here, and you have some multiplicativity also. So the degree k of f, by definition, it's going to be the pullback of omega k dot omega d minus k. So even in the case of rational map of PD, to actually compute these numbers is quite tricky. Anyway, so this is a perfectly well-defined positive number. And you also have some multiplicativity using the same kind of argument here. So degree k of fn times a suitable constant is multiplicative. And so you can define this lambda k of f, which is the limit, applying Fekette's lemma again, of degree k fn 1 over f. Okay. Okay, so now we remember this log concavity. So again, this is here equal to 1. So if f is the rational map, dominant, now what you have is a collection of real number, which is some kind of a spectrum attached to this, this map, right? So you have lambda 0 of f, lambda 1 of f, lambda 2 of f, etc., lambda d of f. Okay, so here, if you look, sorry. Yeah, so it's 1. It's always 1. Okay, so you look through the definition, and then you get, here is a constant, so you divide by, you take in 1 over nth root, it's always 1. So what? Sorry? Are they called second, third dynamical degrees? You can, yeah. Yeah, the first, so this is the kth dynamical degree, lambda k is kth dynamical degree. Who is this guy? This is a topological degree. In the sense that if you take a sufficiently general point inside X, you count the number, so it's preimages is finite. You count the number of preimages, maybe with multiplicity, and you get exactly that number. Okay, but in between is much more mysterious somehow. So there are a lot of work in the case of, let's say, surfaces on how to compute lambda 1 of f. What is lambda 1 of f is birational. It's a very specific, so it's either quadratic or integer or a Salem number and so on and so forth. There are many, many work about this. Okay. It's a dimension of the space, yeah. It's an identification of the, so you can, so it's a rational map. So you might have point of indeterminacy. It also, you might have curves that are contracted. So I've seen that many things can happen, right? It could be a pseudo-automorphism, for instance. So, okay. But so here what I'm saying is that if you take a general point inside X, it's a preimage, it's a finite set. You count this number, and this is what I call the topological degree. Okay? So it has a nice topological, or I mean, yeah, topological interpretation if you want. Is it clear or? Omega? Yeah, okay. Yeah, my spelling is so bad that, yeah, okay. So this is degree index k. This is Fn. So what is the problem? This is n, 1 over n, limit. 1 over n? Fécateur, 1 over n. Okay. Okay, so remember the log concavity. The log concavity says that these degrees, so you see you have f star omega k dot omega d minus k, and then you're shifting k. So in fact, there's this degree index k, they are log concave. So it implies also that the dynamical degree are log concave. So this sequence is log concave. So in particular, it means that lambda 1 to the square is greater or equal to the product of the two neighbors. So lambda 1 to the square is greater or equal to lambda 2 times lambda 0, which is 1. Okay, okay, so yeah, maybe before I state the theorem, yeah, so let me write it down. So the key problem in algebraic dynamics, one of the key problems, is to describe this sequence or these sequences. So it's not clear what does it mean to describe. In general, it's very hard to compute, even in concrete examples. So maybe you want to at least have some asymptotics about this. So you have several variations about this question. So maybe you want to compute this dynamical degree. Maybe, so you see that the dynamical degree is the limit of this thing. So you could expect that, in fact, the degree of Fn is something controlled by lambda to the power n. So maybe give an asymptotic, so prove that, I don't know, degree k of Fn is equivalent to some constants like lambda k to the n. So we know it's not true in general, so maybe give some sufficient condition for it this is true. And if you're even more optimistic, then you want to prove that if you look at the power series like this, so prove that this is rational, etc. So you can ask many things about these dynamical degrees, and we know. So in dimension 2, the story is quite well understood now, especially for birational surface map. It's essentially complete. But even for non-invertible surface, rational surface map, it's quite open. So here I want to state one theorem, which is true in any dimension. So again, it's due to Dong and myself. So it states that if lambda 1, so this, if you have a strict inequality here in this log concavity statement, then in fact you can answer this. You can answer this question. So here we don't know, and here we don't know also, but at least what we know is that there exists some positive constant, C, and there exists some mu less than lambda 1, such that the degree of Fn, so I should put like degree 1. It's very much controlled by lambda 1 to the n, and maybe you have some error which is bounded by mu to the n, so it decreases exponentially fast compared to this lambda 1. Okay? Okay, so in the remaining, I don't know how many minutes I have. I'd like to, 29 or 28.35 or something like this. So I'd like to explain to you why B-divisors enter in a crucial way in proving such a statement. Okay? Okay, so first, so to try to understand, I mean, what lies behind this is we need to discuss the case where F is not rational but is a morphism. So let's discuss, let's assume first that F is a morphism. So no point of indeterminacy, regular, dominant. Yeah, well, it's going to be. Okay, so how do you prove such a thing when F is a morphism? Well, the idea is to look at the action of F on the narrow Savary space, the real narrow Savary space, which is a finite dimensional vector space. Okay, so this is a linear map. And we're going to look at the spectral properties of this map. And, well, lambda 1 and these numbers are going to appear naturally when we look at the spectrum properties of these guys. Okay, so we need to compute norms and so on. So I'm going to fix any norm. Let's say double like this, a norm on N1 R of X. And I'm going to play with the NEF classes. And so I need to relate the degree of F to the norm of the operator of F star. So recall that, so the norm of the operator, what is this? This is a supremum over all classes like this of the norm of the pullback divided by the norm of alpha, okay? And what I claim is that, in fact, this number is up to some uniform error is exactly this degree. So how do you see that? Okay, so, well, okay, maybe I claim, let me write it down. So there exists some constant such that for any integer, n, the norm of this operator is, in fact, controlled by the degree uniformly. Okay, so it's not very difficult. Let me just say one thing is that, remember, so lambda 1 is the limit of this degree of fn to the power 1 over n. And so it's also, because of this lemma, this is the limit as n tends to infinity of the norm of the nth iterate to power 1 over n. Okay, here I wrote this way, but this is the same as this. And what you see here is what is called the spectral radius of F star. Usually it's denoted by rho of F star. What is it? This is a supremum of the modulus of all eigenvalues, maybe lambda, of F star. Okay? So just this lemma gives you some kind of spectral interpretation of this number lambda 1. So how do you see this? You look at the NEF cone. So for me, the NEF cone is always round for some reason. I know this is maybe not, from a geometric point of view, maybe not the more interesting stuff, but okay, so this is an F cone, and the claim is that there is a, so you have this norm, but in fact, if you take a class alpha, which is NEF, the norm is essentially the intersection with the ample class. So remember that from the very beginning, we have some ample class omega on X. So there exists some constant such that, well, the norm alpha, so with respect to this norm on N1, or maybe I should say like this. In fact, it's the same as looking at the intersection with omega d minus 1. Why is it so? Well, you cut by, you slice it like this, it's compact, and you look at the function omega dot omega d minus 1, it's always positive. In fact, this is true not only in the NEF class, in the NEF cone, but also in the pseudo-effective cone. But anyway, we're going to use it only for the NEF cone. So now that you have this, I think this implies this almost immediately. So now I don't see it because I'm too close to the board, but so yeah, you applied this inequality to Fn omega of omega divided by Fn of omega. So this is what, yeah, okay, well, sorry. So this is bounded by C times this norm, which is bounded by C times the norm of omega times the norm of Fn to the star, and this is the degree of Fn. Okay, so this gives you one bound, maybe this lower bound. And then, okay, I don't know, but this lower bound here gives you the other bound. Okay. Okay, so it's good. So remember, I want to prove something like this. So this tells you that, here, this degree of the iterates, so proving something like this says that, in fact, the spectrum of this linear operator on N1 is very special. So this statement here, blue. It's equivalent to say that, let me just draw a picture. So if you look, so this is a spectrum of the pullback of F. So, well, so you need to have lambda 1 that appears somewhere here. And in fact, all other eigenvalues are somewhere here in a disk of reduced mu. And even more, if you want something like this, you need to prove that lambda 1 is in fact a simple eigenvalue. Okay, let me explain what it is an eigenvalue. It's an eigenvalue because, in this case, we know that the Neff cone is preserved by pullback. So if you look at this linear operator, F pullback on narrow Severy classes, it preserves this strict closed convex cone. And then this is a general theorem called, referred to Perron-Frobenius, at least in France, which tells you that if you have a closed convex strict cone, which is preserved by linear map, then you can always find one invariant class, let's call it theta, which is attached to the eigenvalue. Well, okay, so I should say this way. So first, so when I have a cone which is preserved like this, first the spectral radius is an eigenvalue, and in fact you can find an eigenvector which is attached to this eigenvalue. So there it is theta Neff, such that the pullback of theta is equal to lambda 1 theta. Okay? So this is a finite dimensional story. And now so I'm not sure I'm going to be very precise here, but so the key ingredient here so this statement is valid for any rational map. So I think for morphism it was obtained by Thuyen a couple of years ago. And so the key to go to remove this assumption on F to be irregular is to play with the B classes. Okay. So let me explain. So we're going to do exactly the same thing, except that now the pullback is not going to work on N1 of X, but N1 of script X, which is infinite dimensional. And so here the first problem is, okay, which norm I'm going to play with. Okay, and this is, let's say, the key to this theorem is to introduce the right norm for which we can develop all this analysis here. So, okay, here I didn't say, but the fact that this is simple, it's a Hodge-Index theorem. Okay, so let me give you like a flavor of what's happening here. Okay, so yeah. So now F is rational. So we want to look at the pullback operator, and the first thing is that, in fact, this pullback operator acts naturally on Cartier classes. yeah, just to, yeah, I could just continue like this and you would just believe me, but let me take like 2 minutes to at least convince you that this is the natural functor properties, like pullback on Cartier classes. So take a Cartier class alpha. What does it mean? It means that, so you have f from x to x. So this means that there exists some model x pi over x such that, in fact, alpha is the Cartier class attached to alpha pi. So it's determined by this class in x pi. So when you have a birational model like this, what you can do, you can always resolve the singularities of your map F. So you choose a model x pi prime such that this map here is a morphism, is regular. You can always do that. And how do you define the pullback of alpha? So remember alpha, this is a Cartier class attached to alpha pi. Well, what you're going to do is that you're going to pull back alpha pi by this capital F and take the Cartier class of this. So this is a definition. And you need to check that this does not depend on the choice of capital F and the choice of x pi that determined alpha and so on, but this is like a routine check. Okay. Then there are some claims. Not completely trivial, but what you can do, what you can show is, in fact, that f, the pullback, extends the natural map, linear map, from the space of Y classes to itself, and it's going to be continuous for the natural topology, for the locally compact topology. The only problem is that this topology is not, how do you say, is not determined by some norm. So Wn1 is not a Banach space in general. And in fact, it's too big. So the idea is to restrict this F star to a much smaller subspace. And the natural thing to do is to look, so as we saw in the case F is regular, then the invariant classes, at least the most important invariant class is Nef. So what is natural to do is to restrict to the Nef cone. Okay, well, Nef cone is a cone, it's not a vector space. So it's to restrict to the vector space, which is generated by the Nef cone. Okay, good. Fine. So it contains observation. It's quite big, right? It's in fact dense in this guy. It contains all Cartier classes. Now I'd like to say that this guy is, so pull back, preserve V, maps V to V, because Nef classes are preserved. So this is fine. But now the claim is that V is a Banach space. It's a natural Banach space. For which norm? Okay, well, on V maybe it's not clear, but what will be the norm on the Nef class? So suppose alpha is Nef. Well, we know this. We use, as before, we intersect with our favorite ample class inside X, alpha. So you set alpha, the norm of alpha to be alpha omega d minus 1. So you have to, so this is linear, this is positive and 0 if and only if alpha is 0. So it's easy to check that this is a norm. And you extend it to V naturally in the sense that if alpha now, or maybe alpha prime, okay, sorry, if alpha is any class in V, what will be the norm? Well, you look, since it's in the vector space generated by Nef classes, it can always be written at a difference of two Nef classes. Okay? And so I don't know why I started to write a bracket like this. But you look at the other decomposition of alpha as a difference of two Nef classes, and you take now the infimum of the norm of alpha plus and plus the norm of alpha minus. Okay, great. Yeah. Okay, so now the claim is that if you look at the pullback operator from V to V, in fact, it's a bounded operator. Okay, maybe I didn't say it, but so maybe you have to check it first. Is that so? This is a norm on V. When I say it's a Banach space, it means that in fact for this norm, V is complete. It's not completely clear, but in fact it's so. Yeah, there are going to be like more and more exercises from now on. So yeah, it's a direct check also. Okay. So what you do is that you have a Cauchy sequence for this norm, and so it's going to be a Cauchy. I mean, you have a decomposition like this for which this alpha plus alpha minus on both nef, and you have like Cauchy sequences also, and then you use the fact you can extract subsequences that are going to converge because the topology is locally compact. And you get the limit like this, and you have to prove that it's converging norm, etc. So, but it's not so difficult. So it's a Banach space, and the pullback is bounded operator. So why is it so? Well, it's so let's suppose that alpha is nef, and what you want to do is you want to estimate the norm of the pullback of alpha. What is this? Well, this is a pullback of alpha dot omega d minus 1. And you want to estimate this in terms of the norm of alpha, which is alpha dot omega d minus 1. Okay, so you see that here you can use again Su inequality. So it tells you that since alpha is nef, that alpha is less or equal, it's less effective, that d times omega times alpha omega d minus 1. Okay, take the pullback. And then cup with omega d minus 1. And so you get exactly that this is bounded by d times the degree of f times the norm of alpha. Okay, so I'm repeating, in fact, the same argument as before. And so here, what it says is that, again, so not only f is bounded operator on V, but also that there exists some universal constant such that, well, depending on omega and d only, that the norm of this operator, maybe here of Fn, divided by the degree of Fn is bounded from above and from below by some universal constant. And so, again, this lambda 1 can be interpreted as a spectral norm. But now, it's not a finite dimensional vector space, it's an infinite dimensional Banach space. Okay. So how about the Perron-Frobenius theorem? Well, it works approximately the same. So since the pullback preserves the nef cone, which is closed and convex and strictly convex, then again, there exists some nef class which is attached to lambda 1. So maybe I'll give a hint on how one can do that. So at this step, we are still kind of far to prove such a thing, but the next step, which I'm not going to tell too much about, is to exploit this condition to show that, in fact, theta is a simple eigenvalue. And here the story starts to be, in fact, this is the beginning, it starts to be quite difficult because kind of involved. Because here you need to use some kind of Hodgkin theorem plus some compactness statement, and it turns out that V is not the right space to work with. So too bad for us. But you need to work with some other space that we denoted by n1 sigma. And just to make the connection with what Susanna was telling us, I think, yesterday, is in dimension 2, this space is usually called the Picker-Manning space. So it was introduced by Cantar on his work on the Cremona group, at the same time by Buxton, Johnson, and myself. Okay, so yeah, there are a lot of information around here. So maybe in the time remaining, I explain a little bit how you do this. And yeah, well, I could continue, but I guess it's like yeah, sufficient for the day. So this is completely classical, right? So you have operator, which is positive in the sense that it preserves, on the Banach space, it preserves some cone, etc., and so on. But yeah, I find the proof interesting. So yeah, well, hopefully. So it goes like this. So you consider the following series. So T is any number, real number. It's going to be less than 1 over lambda 1 and non-negative. And so you look at the following series. So sum of Fn omega T to the n. Okay, so if you stop the summation at some finite level, you have, so these are, so you view them as Cartier classes, which are nef. Okay? So this is a sum of nef Cartier classes. So if you stop at the finite level, this is a nef Cartier class. So I have to tell you why this series is converging, at least when T is strictly less than 1 over lambda 1. So let's compute its norm. So you have to cup with omega d minus 1. So this is a sum. And here we get the degree of Fn, T to the n. And what you know is that, so you know that degree of Fn to the power 1 over n converges to lambda 1. So this gives you a lower bound. Since it's submultiplicative, you have a lower bound, like C lambda 1 to the n. And you also have an upper bound, which depends on the choice of some epsilon positive, very, very small, lambda 1 plus epsilon to the n, something like this. So if you look at this, then it tells you that this series is going to converge. So yeah, well, so you pick epsilon, and you take t, which is less than 1 over lambda 1 minus epsilon, plus epsilon maybe. And then this estimate is going to tell you that this series is going to converge. Okay? So theta of t exists for any t in size 0, 1 over lambda 1. And then let me use this lower bound. So what you see here is that theta t omega d minus 1 is greater or equal to the sum, constant, lambda 1 to the n, t to the n. So this is like c over 1 minus lambda 1 t. Okay, so what you see is that, so for t in 0, 1 over lambda 1 excluded, this is a perfectly fine nef class. And when you convert to 1 over lambda 1, the norm is going to explode. Okay. So let me do one more computation. So if you pull back theta of t, so what do you get? So sum n non-negative, f n plus 1, pull back omega t to the n. Okay, so this is something like 1 over t, sum from n non-negative, f n plus 1, omega t to the n plus 1. So this is essentially theta of t up to some, so you're forgetting one element here. So it is sum from n greater or equal to 1, fn star omega t to the n. So 1 over t, it is theta of t minus omega. Okay? Okay, so now we're in business in the sense that what you're going to do is you look at theta of t divided by its norm, and you let Tn goes to infinity. So you take a sequence Tn that increase to lambda 1, such that what? So this is a sequence of Neff classes, but of norm equal to 1. So this is a compact set, and so you can always extract a subsequence such that this converges to someone. Let me call it theta. Okay, so when you go, you let this Tn tend to 1 over lambda 1. You divide by this norm. You know that this norm is increasing. It's going off to infinity. So when you divide by the norm, it's going to kill this small error here. Okay? And so what you get in the end is that f star of theta is 1 over t goes to 1 over lambda 1, so to lambda 1 t, theta. Okay? And this concludes the proof of the existence of such an eigenvector. And I guess, yeah, I could continue, but maybe, yeah, well, okay. I have 2 minutes remaining, so yeah, I think I'll stop here. Thank you.